Good evening and welcome to Electron Exchange. With your favorite host, I'm Derrick on.
And I'm Joshua Park, here to bring some of chemistry's most charged conversations.
This podcast was brought to you by the Miss Tran Association, dedicated to getting you a 5 on AP Chemistry.
As the saying commonly goes, opposites attract and likes repel. Well, where exactly does the statement come from? In chemistry, we call this attraction or repulsion for the Coulombic force.
If we examine the periodic table, all 118 atoms are represented in the most neutral form, meaning there is an equal number of protons and electrons. And because protons and electrons are positive and negative respectively, each atom has a net charge of 0.
However, many of the elements found in nature are actually what are called ions, meaning they are slightly more positive or slightly more negative due to the greater number of either electrons or protons.
Correct. And ions can either go two ways. A greater number of electrons makes it a negative anion, and a greater number of protons in the nucleus makes a positive cation.
So electron affinity then is the energy released from a neutral atom when an electron is added to an atom's outer valence shell to form an anion. Due to a neutral atom's initial net charge being zero, adding an electron would actually release energy, and this is measured in kilojoules per mole.
Wait, so this just sounds like the exact opposite of the first ionization energy trend, which is the amount of energy required to take away an electron from its valence shell to create a positive cation.
Correct. And so there is a neat little trend on the periodic table that we could determine intuitively. As we go from left to right, electron affinity increases as we see a decrease in atomic radius and a greater Coulombic force of attraction.
And so inversely, it must decrease as we go down each period due to an increase in atomic radii as we add more electron shields.
There is also an interesting phenomenon called electron shielding that we see as we start adding more electron shells. Electrons in close proximity with each other will actually start repelling one another. Due to this, electron affinity or energy release will naturally decrease as there's more electron shielding and repelling from the nuclear charge, which is positive.
Indeed, and because electron shielding only increases with more shells, electron affinity will promptly decrease, creating an inverse relationship.
We could observe this using evidence from the periodic table itself. Lithium has an electron affinity of negative 60 kilojoules per mole, while fluorine has an electron affinity of negative 328 kilojoules per mole. As you can see, going left to right across a period usually results in more energy being released.
Does this trend hold true for the entire way across?
Not quite. You see, for elements in either the second group or the eighth group, adding an extra electron to form an anion does not release energy, therefore making the electron affinity almost zero.
But why these two groups in particular?
Let's take a look at the element beryllium, which is in the second group. Its electron configuration is 1s2, 2s2, meaning two subshells of electrons are completely filled.
So adding an electron would need to open up the next p subshell, which would actually take more energy than it's released.
Indeed, this is due to Coulombic forces of repulsion from the first two subshells, shielding the force of the nucleus from the newly added electron, which is now in a new subshell.
Oh, I get it. So a similar thing happens to elements in the eighth group. For example, neon, which belongs to the eighth group, has an electron configuration of 1s2, 2s2, 2p6. As a result, there is basically no energy released when forming an anion, because to do so would be to add an electron to three levels of completely filled up subshells.
Correct. Another exception would be the element nitrogen. Nitrogen has an electron configuration of 1s2, 2s2, 2p3. As you can see, the p subshell is half full, lending it extra stability.
I see, and due to Pauli's exclusion principle and Coulombic forces of repulsion, electrons will want to fill up the available orbitals in the same direction before going back and filling up the remaining orbitals.
So to add an extra electron to a nitrogen's already balanced subshell would mean you need to add one electron into an orbital that is already occupied, leading to more repulsion.
Hey, I have something to tell you now.
What is it?
Did you know that many Americans should actually thank electron affinity for saving their lives on more than one occasion?
How so?
Well, many smoke detectors and carbon monoxide detectors rely on the tendency of some elements to capture electrons and release energy.
That is so awesome. I never knew that.
Well, we talked about enough about the energy released when an electron is absorbed. Now let's discuss something about a little different but related. An element and its likelihood of actually absorbing an electron to form a cation. A lot of people release energy and are pleasant to be around, like the nonmetals with high electron affinities. Some people in life naturally attract more people than others. Likewise, this is also the case in atoms.
Electronegativity is a measure of an atom's ability to attract electrons in a chemical compound, different from electron affinity, which measures the energy released upon absorbing an electron.
And according to Coulomb's law, as ionic charges increase, the forces between charges will also increase.
With a decrease in radii, electron density increases, which increases electronegativity charges.
We can conclude that greater nuclear charges and closer radii between the nucleus and the valence shell will lead to stronger attraction within the atom.
Now that we know what happens in electronegativity, how do we measure it?
I heard that electronegativity has its own measuring scale called the Pauling scale.
Can you explain what the Pauling scale is?
The Pauling scale determines how electronegative each element is, with francium being the lowest at 0.79 and fluorine at 3.98, essentially meaning that fluorine has the greatest degree of attraction.
Have you heard that electronegativity has a periodic trend, much like electron affinity?
There must be a trend, right? Wouldn't the trend consist of elements increasing in electronegativity across the period and upwards on the group, since francium is the lowest?
That's correct. Although there's a misconception that noble gases have the highest electronegativity out of all groups.
Why not? Aren't they group 18 the rightmost group?
Noble gases already have a full valence shell. This makes them unwilling to form any chemical bonds, and therefore their electronegativity value cannot be determined.
Well, that makes sense. But why exactly does electronegativity increase across the period and upwards on a given group?
Since metals have fewer electrons than nonmetals, when a metal forms a bond, they lose electrons to become a cation.
I see. So metals would have lower electronegativities and non-metals like halogens, group 17, would have the highest electronegativities.
We know what electronegativity is, but what is it really used for?
Well, chemists have used the Pauling scale values to determine the difference between electronegativities of two elements in a certain bond.
What does a difference represent?
Typically, in an ionic bond consisting of a metal and nonmetal, the difference is called the polarity.
Polarity?
Yes, polarity is the distribution of electric charges of an atom inside of an element, and it's determined using the difference in the Pauling scale values of the two elements.
Oh, since ionic bonds have a nonmetal in the middle, the polarity as a result of the large difference in the electronegativities must be greater than a covalent or polar covalent bond.
That's absolutely correct. Moving on, how do we incorporate electronegativity into our daily lives?
Do you know what Teflon is?
No, please entertain me.
So Teflon is a polymer that coats the non-stick pans you often see in commercials and is a fluorocarbon, or carbon in case of fluorine. Earlier, we talked about how fluorine has the greatest electronegativity out of all elements, and the properties make it highly unreactive.
Wow, really? I didn't know that. Speaking of applications in real life, have you ever heard of pharmaceuticals using electronegativity?
I've heard of it, but why?
Many medical drugs are in the picometer range, so it's really small. So, electronegativity is implemented to make these drugs specifically interact with only specific proteins. A certain intramolecular force value is assigned to a drug or tuned to match the protein's receptor.
It's very cool to see a concept as unexpected as electronegativity to be so common in our daily lives.
I agree. Well, that wraps it up for today's Electron Exchange with your hosts. I'm Derrick on,
And I'm Joshua Park,
brought to you on the live thanks to our sponsor, the Miss Tran Association.
dedicated to getting you a 5 on AP Chemistry. Stay as positive as a cation.